Okay, good. Are we online? Do you guys hear me? Yeah, doesn't seem like. Okay, maybe now you hear me. Okay, great. So lecture for today will be quite exciting. So yes, last week Baharan was teaching on Thursday. I was away traveling, giving talks. And she talked about optimizing submodular functions and thinking about this notion of influence maximization in networks using independent cascade model and things like that. And today's lecture will also be about submodular functions and machinery that we learned in the last lecture. But the idea will be that we will work in a different problem, which this problem will be kind of the reverse of influence maximization, which is about outbreak detection. And the idea is the following, right? We will define the outbreak detection problem in this lecture, and then we will also define or develop an approximation algorithm to solve it that will be, again, a submodular optimization problem. And then in the last lecture, we talked about using greedy hill climbing algorithm to identify what nodes, what cascades to select. Here we will also use the same algorithm, but we will further speed it up. And then we will prove a new bound that will tell us what is the quality of our solution, right? So what we did on Thursday was that we showed that for optimizing non-negative submodular functions, greedy hill climbing algorithm gives us this 63% optimality guarantee, right? So 1 minus 1 over E guarantee of the quality of optimal solution. What we are going to do, and notice that that bound was data independent. It was basically said, however ugly, however adversarial data you get, the algorithm gets, greedy will give you at least this, greedy will work at least this well. Today, we will show what is called a data-dependent bound, where we will look at the algorithm and the data to provide a certificate for the optimization quality of our algorithm. And this data-dependent bound will basically say, however, you can find your solution however you want, but here is a certificate how good your solution is with respect to this optimal solution that is too complex to compute. So that's the idea for today. So what is intuitively the problem definition? So the problem definition actually comes from a real-world scenario, and this was actually the project I was working on. And the project was the following. You have a city water distribution network, right? So you have houses, and you have physical water pipes between these houses. It's how the water comes into the buildings, right? You have a network of how the water flows. And then mechanical engineers, they have a lot of simulators that simulate how the water flows across these pipes as people wake up, take shower, go to work, come back, cook dinner, I don't know, do more shower, wash their teeth, watch television, and so on, right? So there is this complex flow across this physical water distribution network. And the idea is that at any point in time, there might be some contamination happening in this network. And the question is, where should you pose your sensors so that you can detect these contaminations as quickly as possible? And this was really the problem that US Environmental Protection Agency deeply cares about, right? So the idea is, if I have a network, and perhaps there could be an outbreak, a contamination starting at one site and kind of spreading throughout the network over time, and that's maybe one contamination. So if I would decide to place a sensor here, and perhaps a contamination would to start at this house, it would spread and spread, and as soon as it hits my sensor, I raise an alarm and say, here, stop, something is happening. So this is the idea of outbreak detection. I want to detect that an outbreak or a cascade is happening throughout the network as early as possible. And if you pose it this way, then here's a realistic, very useful use case, right? Imagine we are all following social media, we are all following Twitter and things like that. And the way you can think of information on Twitter would be the following. You could imagine that there are different accounts, different people. For the purpose of this, let's call them users, or let's call them blogs. And each user has a number of posts, right? And sometimes these posts get retweeted or get reposted. So you can think that a given post is kind of spreading throughout the Twitter network. right? And this is now an information cascade, right? It's like a resharing, retweeting behavior throughout this network of blogs or a network of user accounts on Twitter. And of course, what would I like to do? What I'd like to do is to say which users, which accounts should I follow so that I am most up to date, right? I want to detect these big information outbreaks as soon as they happen. Who should I follow to be most up to date, right? So that whenever there is some big news happening, I'm not the last guy to learn about it, but maybe I follow someone else and I'll be the first to learn about this news, right? So how you could think of this, you could think that you have a certain set of blogs, they post information, the information cascades through the rest of the blogosphere, there is different pieces of information that cascade in different ways. So now the question is, who should I follow, right? I want to read or learn about important news before others do. So for example, I could follow this blog. What is good about it is I would learn about all these 3 different stories, but I'd be kind of the last person on earth to learn about it, right? While, for example, right, so here I would detect all of them, but late. But maybe if I follow this particular blog up here, I would learn about blue and yellow immediately, right? But I would get to totally miss the red story. Okay, so that's kind of the trade-off we'll be talking about, right? So here I detect blue and yellow, but totally miss the red one, but I detect blue and yellow very early, rather than here, where I detect everything. I get to learn everything, but it's so late that I'm the last person on earth to know it. You had a question.
A lot of news outbreaks like this would happen with unstructured data. Do we have to work with a limited set like hashtags or something like that?
So the question is, how do you detect these information cascades? You can detect them different ways, right? So for example, many times these things can be explicit by people resharing or reposting. Many times you can just follow the hyperlinks, how they get created and who's linking to whom. And that's why these arrows are pointing up, because this means that this guy is pointing to that guy, is pointing to someone else, right? So you can kind of reverse track the hyperlinks. And there is either another approach that basically looks at short snippets of text, and you can think of those as little pieces of DNA that is spreading throughout the news. That's called meme tracking. So there's different approaches. How do you detect? But for our purpose here, this is given to us. Okay? So that's what we'll talk about. So here's the general problem. These were just 2 instances of the same underlying problem, right? Given a dynamic process that is spreading throughout the network, we want to select a set of nodes to detect this spreading process as quickly as possible. There are many other applications, like epidemics is another one. The question would be, if I want to detect a flu outbreak, which people in the human network should I monitor to detect an outbreak as quickly as possible? Or if you'd say network security, again, which machines in the network should I monitor more closely to detect an outbreak as quickly as possible, right? So that's the idea. So there is 2 aspects. Yes?
We are given the network.
We are assuming we are given the network.
How does it apply in the last example? Like there the links created the network. Last slide. The blog post.
Yeah.
The process was itself creating the network, right?
Process was itself creating the network. It will turn out I don't really care about the network. All I care is about infection times of different nodes. So the network is kind of just a medium for the spread of information, but I don't need to see the network. Okay, so you will see the network must. I don't care about the seeing the network. The network can be implicit. Okay, so there are 2 things we will care about. The first thing we'll care about is this notion of utility, right? So the question will be, what is the utility if we place a sensor somewhere, right? So if I think about water flow dynamics, how demands of different households and so on. So this is now a real distribution network of a real city in the United States, right? And you can think of it the following, right? If a contamination spreads, this is now real data. The contamination will affect certain sets of houses. For example, if it spreads here, this is how it, if it starts here, this is how it will spread. Why? Because there's probably a big pump station or a well here. So essentially all these houses get the water from this big pipe. But for example, if a contamination would start here, it would spread differently because this is the edge of the network, so it would just kind of affect a smaller set of the houses. And you know, here's another example where really in the edge of the network, if the contamination starts here, the outbreak is kind of small, right? So here, if it starts here, I would have a big outbreak. Here is kind of medium-size outbreak, and there is a small size outbreak, right? And just to show you, for example, now if for every junction, every node in this network, I would say how big of an outbreak would be created or how many people would get sick if an outbreak starts at a given point. This is now, the red means many people would get sick. And you kind of see this backbone of this water distribution network. And you see if outbreaks start here on the periphery, few people get sick. If they start along the main axis of this water distribution network, a lot of people would get sick. This is what I tried to illustrate with these colors. And now if this is the problem, then the way you can think about it is to say, if I put a sensor here, then kind of the sensor will detect outbreaks that are in the vicinity of it, right? So the sensor will get infected by the outbreak quickly, right? So in some sense, a sensor will reduce the impact of the outbreak by detecting the outbreak quickly. And then we think as soon as we detect, we kind of stop the time, everyone stops drinking water, and nobody else gets sick. That's kind of the assumption, right? So you could think about placing a sensor and sensor detecting the outbreaks that affect it, right? And then what we will want to do is we will want to place multiple of these sensors, and for every placement of sensors S, that is a subset of all possible placements V, we will get some utility F, which is the score that we will care about, right? So for example, maybe in our case, we would want to place the sensors in these positions so that they nicely cover different parts of this water distribution network, right? And this would be, let's say, this would correspond to the high quality of our sensing because it's nicely distributed across the network. But for example, if we were to place sensors like on different locations, let's say very much in the periphery, then these sensors would kind of cover much kind of smaller areas, so the quality of this sensing would be low, right? And I'll make these things more precise, but what I want to convey right now is that what we want to do is we want to kind of place sensors here on the backbone, and we want to make sure that these sensors are kind of non-overlapping. Yes?
So is the intuition here, this kind of area that the sensor is covering, that's the area in which the sensor would rapidly detect an outbreak?
For example, yeah.
I had a related question, because when you're giving the motivation earlier, you talked about like different websites that you could follow.
Yeah.
And one of them was helpful because you could get all of the stories, but the other one was helpful because you could get the stories early.
Correct.
So I was wondering if utility deals with that trade-off between basically like recall, like how many you can get, and precision. Like.
A great question. So what we will have here is we'll have two different, I'll talk about it. And the way we will think about it, there will be a notion of utility, and there will be a notion of cost. And the cost will be that, I know, placing a sensor somewhere might be more expensive than another place. Another way to think of cost in social media is if I follow someone who's posting a lot of posts, that's a lot of cost to me. It takes me a lot of time. So following that won't be as good as following something else. Okay? So I'll make these notions much more precise. Okay? So what are we going to get? We are going to give the graph. And we are essentially given the graph. What we all care about is the data about how the outbreaks spread over the network. So basically, all this algorithm gets is for every outbreak, we want to know the time when that outbreak hits a given node. Okay? And if the outbreak does not hit the node, then that time is set to infinity. Okay? So really, for every outbreak, we just want to know at what time does it hit a given node. And then if it doesn't hit certain nodes, those times are set to infinity. Okay? And then how are we going to obtain these things for the water distribution network? We'll take the real water distribution network. We'll take this mechanical engineers built simulator of how the water flows. And we are going to simulate a lot of different contaminations in this network. And contamination will be defined by the location and time of the day, because the water usage differs across the time of the day. But again, the input is for every contamination, what node gets infected at what time. And now the same will be for the social media, where basically we will be saying, given the network, here are some information cascades, and all we care about is where does the information cascade start? This defines the outbreak, and then what nodes get infected at what times, right? So we'll want to have this set of information cascades, and what nodes get infected at what times. Okay, so that's the input. The input is basically a set of numbers. In some sense, you can think of them as triples of outbreak, node, time. That's what we get on the input. Okay, so now what are we going to optimize? Our goal is the following. Our goal is to select a subset of nodes so that we maximize the expected reward, right? So our goal is find a subset of nodes such that this f of the subset of nodes is maximized. How is this f defined? This f is a sum over all the possible outbreaks, probability of that outbreak happening, and then how well do we detect that given outbreak, right? And this will be now maximizing the expected reward. If all the outbreaks are equally likely, then this will be all 1 over the number of outbreaks. If you have some information that you want to make this non-uniform, you can make it. But you know, a mechanical engineer should tell us how to set this. We don't care. And then given a set of placements, we will need to define how this notion of how well does this given set of sensors detect a given outbreak, right? And this is now the way you can think of this is the expected reward for detecting the outbreak I, and we'll have an interesting twist. The interesting twist is that the cost of our placement has to be less than our budget B. Okay, so we'll have a budget constraint. So the way to think about this is we need to define the reward, and we need to define the cost. There are many different rewards you can define. So here are a few different ones that are kind of orthogonal but related but different, right? One thing you may want to do is to say, I want to minimize the time to detection, right? As the outbreak happens, I want to be the first, I want to detect it quickly. That sounds like a good objective function. Another one, for example, could be to say, I want to maximize the number of detected outbreaks, right? So this one says, I don't care how late I detect, but I just want to know that there was an outbreak, right? This is what Serena was asking. So if I just care about detecting, but I don't care how late, number 2 will give me that, right? And for example, maybe the most realistic one is number 3 that says, I want to minimize the number of infected people, right? So I want to minimize the number of people that get sick. So the idea here is that I want to detect big outbreaks quickly because I don't want too many people to get sick. And I'm fine to miss a small outbreak because it won't hurt too many people anyway, right? So depending on what exactly you want, one of these 3 different objective functions might be appropriate, or some combination of them, and we will work with all 3 of them. Yes?
Couldn't you make an argument for finding what makes a model which maximizes the number of infected people so that you know what weaknesses you can fix with that to ultimately minimize the number of infected people?
So you say identify create a placement that maximizes the number of people who will die.
Right, and then
but if you do that,
to figure out what contributes most to
yeah, the best way to let the most people die is to not place any sensors, right? I mean, it's a trivial solution. It's not what you want, but being lazy is the best thing to do when you want to do nothing, right? I see where you are trying to go with this. One would need to think a bit more clearly to kind of get this trivial solution away. Yeah.
So is this kind of the inverse problem to influence maximization, in that, like, if someone was adversarially trying to infect as many people as possible, they would be doing influence maximization, and you would be doing this?
That's a good way to think about it, right? So it is, as I said earlier, it is almost like an inverse problem, right? There, somebody's trying to create the cascades, and here you are trying to detect those cascades as quickly as possible, right? So, but here these cascades might be created by good people, by bad people, by chance, by nature, somehow, right? So objective functions will consider 3. They are different, and they give you different trade-offs. And then we'll consider cost, where cost, you can think of it as a monetary cost, right? It will be reading a big block takes a lot of time, so that's a time cost. Placing a sensor at a remote location might be more expensive to you, right? So the idea is that I have a network. Every node in the network will have cost. We will have out information about a cost of all the nodes in the network. So this is the cost of placing a sensor. We'll be given an outbreak that spreads throughout the network in some way. And the question will be, where do I want to place my sensors to detect this outbreak as quickly as possible? To give you now an idea, for example, if I would say minimize the time to detection, then time to detection here in my case would be 3, because this started at time 1, this guy got infected at time 3, so now time to detection is, let's say, 2 time units. So I'm trying to detect this as quickly as possible. Then, for example, maximize the number of detected propagations. I would just say, I detected this propagation, whether I detect it here or here, it doesn't matter. I get to detect it, I get a reward of 1. And then minimize the number of infected people is essentially saying, here, you know, two people got sick before I detected, so I'm okay, right? Or that's my penalty in this case. Or another way to say is, oh, I saved all these people because I detected these positions. Okay, so that's the way to think about these different functions. So let's now formalize them. The way we will formalize them is we will formalize them as penalties. Okay, and then here is how to formalize these penalties, where we will basically only consider one outbreak at a time. Because if we can solve for one outbreak, we can then solve for the sum of them. So the P sub I of t means what is the, I have a pointer, right? It says, what is the penalty for my placement of sensors to detect outbreak I at time t, right? Time to detect says how long does it take to detect a contamination. So penalty for detecting at time t would be simply equal to t, right? So if I detect outbreak at time t, then the penalty I incur is t. The bigger the t, the more penalty. Then detection likelihood says, if I detect, I get 0 penalty at any time t, and if I don't detect, which means that I only detect at time infinity, I get penalty of 1. Okay? So here, this is a binary outcome. I either detect or not. I don't care when. And then population affected, you would say, the way you could think of this penalty for detecting at time t is the number of infected nodes that in the outbreak I by the time t, right? So I'm asking how many people got sick up to the time when I detected the outbreak I. Okay, so these are now these penalty functions pi, how they are defined depending on what objective function we want. Notice that all these objective functions are monotone. What does it mean is that the sooner, if I detect sooner, it does not hurt, right? If I detect sooner, pi in the first place will only be smaller, right? That's great. If I detect sooner here, it doesn't hurt because I only get penalized when I don't detect, right? And then down here again, detecting sooner will only help because fewer people will get infected. So it means detecting sooner never hurts. It may only help, which means that objective functions pi are non-decreasing. Right? The penalty only increases or stays the same or increases over time. So they are monotone. Okay, so that's the first important thing. The second important thing is that our f will be the notion of penalty reduction. Okay, so what we will want to maximize now is the penalty reduction. And penalty reduction means for outbreak I, here, for a penalty reduction for outbreak I is the penalty for not detecting the outbreak minus the penalty of detecting outbreak I at a given time, right? And capital T of sensor placement S for outbreak I is the time when this got detected. And now this is the penalty for detecting at that time, and basically the reduction in penalty is penalty for not detecting minus the penalty for detecting. Okay? And we'll try to maximize the reduction of penalty. The reason why we formulate this way is because now we will be able to prove that f is submodular. Maximizing pi is not submodular, but maximizing or minimizing pi would not be submodular, but maximizing f is a submodular function. So observation is that this f will have this diminishing returns property, where basically the idea will be, if I already have some placement, and this placement covers some part of the network, if I consider adding a new sensor, this new sensor will cover some new area, and the benefit of this sensor will be a lot. While if I have, let's say, a bigger placement, a superset of it, where before x1 and x2, I also have 3 and 4, and now I consider placing, let's say, the sensor at the same position. Now, a lot of this coverage will already be covered, so this sensor x prime will help me less. Okay? So this is this notion of diminishing returns. So here, adding the same sensor helps less. And that's the notion of diminishing returns or submodularity. So let me make a claim and then show you the proof. So our claim will be that for all A, a subset of B, a subset of the vertices V, and given a sensor X, then we get this diminishing returns property that says that adding the marginal benefit of adding X to a subset, to a small placement A, is bigger than adding the same sensor X to the superset, to the larger placement B, where B is a superset of A, right? And what we will show is that all our objective functions are submodular, right? And all we have to do is we have to fix the outbreak I, so we only have to consider one outbreak at a time and show that f sub I of A is submodular. Okay, so all I care about is proving that detecting one outbreak is submodular. And then I'll tell you why detecting all outbreaks is submodular as well. Right? So what I'm considering is a small placement, a superset of it, so a bigger placement. And then the question is, when does this vector, this sensor X that we are considering adding in, so this sensor X, when does the X detect the outbreak I? And there are three, right? We know when the sensors in A detect the outbreak, we know when sensors in B detect the outbreak, and now we are asking ourselves, when does this sensor X detect the outbreak? And there are three cases, right? X can be the first, X can be in the middle of A and B, or X can be after A and B, right? So we need to analyze these three cases separately. So let's say that X detects late, right? So first the placement B detects, because it's a big placement, then placement A detects either at the same time or later, because A has fewer sensors. So this should be clear why this inequality holds here, right? And now I'm assuming that X, the sensor X, comes and detects the outbreak last, right? Detects it after both of the two placements. So what does this mean? This means that X is a useless sensor. So f of A union X is just f of A, and f of B union X is just f of B, because X is useless, right? So what does it mean? This means that f of A union X minus f of A is 0, and f of B union X minus f of B is also 0. So I get zeros on both ends, so my inequality is satisfied, right? So first case solved. We have two more. Okay? So number 2 is that X happens in between, right? Again, placement B is a big placement, placement A is a smaller placement. Because of monotonicity, we know that B only detects, or we know that B cannot detect later than A. Because B has more sensors, it will only detect at the same time or earlier. And now we are assuming that X is the sensor that detects the outbreak between what sensors in B can do and what sensors in A can do. And then what does this mean? That X detects sooner than any node in A, but after a node in B. So X only helps to improve solution A, but not B. So this means that f of A union X minus f of A a positive, will have some positive value because X is now detecting sooner than what we were able to detect before. But because B was the first to detect, f of B union X is the same as f of B, so this thing will be 0, right? Because X does not detect before B, so B remains unchanged, right? So again, this is greater than 0, and this is 0, so again, our inequality from submodularity holds, okay? And now, the last case, which we need to analyze, which is the X, sensor X detects the first, then it's B, and then it's A, right? And I should ask you a question. Shouldn't there be another case where we would say that maybe X detects first, then A detects, then B detects? Why shouldn't I analyze that case? Sorry?
Oh,
Yeah.
because A can't be better than B.
Great. Why can't A be better than B?
A is a subset of B.
Exactly. A is a subset of B, right? And if I'm detecting, then placing more sensors never hurts. So B contains A plus some other stuff. So it will only be better, it won't be worse, right? Great, thank you. You guys are following. All right, even though I was a bit sneaky. So great. So what happens in this case, right? So in this case, the following will happen. The way you can think of this is the following, right? Like, let's just write this out. So what is this? We are saying if X is the first to detect, then f of A union X is the penalty reduction of not detecting minus detecting at this time minus f of A. And now, right, what I want this to be greater than equal than, again, the penalty reduction for detecting this at time X. This was the, but this is now the penalty, this type of penalty reduction. So I'll actually get the same value as I get it for A, because it's the X is the first sensor to detect. But here I have minus f of IB. Why is this thing true? This is true because due to the non-decreasingness of f sub I, right? I know that f sub I of A is less than f sub I of B. So if I have this thing be the same on both ends, and I subtract a small number, and here I subtract a big number, then this thing here will be bigger than that thing here, right? So that's why this is true. Yes?
Could you explain again why we repeat that term on the third line?
Oh, why is this repeated? Aha. So what am I trying to do? I'm trying to, so this term is expansion of that term, right? So if f of B union A. But because X is the first to detect, f of B union A is just this guy detected and the time stops. So in some sense, f of A union X minus f of A is the f of A union X and f of B union X are the same because X is the first to detect, right? So the rest doesn't matter. Good question. All right. So now what we saw is that in all these three cases, this submodularity property is maintained. So this means that f sub I of function f sub I is submodular. Now our function f is a non-negative summation of f sub i's. So if f sub I is submodular, then the sum of submodular functions is also submodular. So from the fact that individual f sub I is submodular, then the non-negative combination of submodular functions is also submodular. And that completes the proof why this thing is submodular. Okay? Good. Any questions maybe now? Yes?
Of I of A is less than f of I of B because A is entirely contained by B, and therefore
no, f of A is bigger than f of B because A is smaller placement. Right? It's penalty reduction. It's not.
Non-decreasingness of f of L. Could you explain that a little more?
Aha. What do I mean by this is basically by adding more sensors, I will detect earlier, so my penalty reduction will only be bigger. Right? So we are kind of flipping from decreasing and decreasing penalty, increasing penalty reduction. Right? Good point. Anything else? All right. Good. So now we established that we are solving a submodular optimization problem. So now let me tell you how what we already know. What we already know is that the greedy hill climbing algorithm gives us this optimization guarantee, right? We know that if we run greedy hill climbing, the same thing as we talked last time, then we will be at 63% of optimal at the worst case. We might be better, but we'll never be worse than that, right? So we have some kind of certificate where if somebody says, hey, greedy, how good job do you do? You're like, here is, I never do worse than that. Okay, so that's the certificate we have. But there are two buts here. The first but is that this thing only works for the unit cost case, right? For the cardinality constraint, which we had last time, where we said you can select k nodes. So the same way you could think of this is to say all nodes cost you $1 and you have k dollars. That's what this worked last time. For us, each sensor has a different cost, so the greedy won't work. I'll show you example why. And then there will be a second issue, is that this greedy hill climbing is actually slow. Why is it slow? Is because at every iteration we need to reevaluate marginal gains of all the nodes. So the complexity to place k sensors is number of locations times k, right? And this can be a lot. Because you can have a network with, I don't know, 1 million nodes, and you want to place 1,000 sensors, so you are doing 1,000, so that's 1 billion operations, right? So it's a lot. So let me try to demonstrate visually this second point, right? So if I have a network and I want to decide the placement, first I need to say, what's the first sensor to put, and I evaluate the F, the benefit, the cost reduction, the penalty reduction for every sensor, and I would pick the best one and place it. And now in the second iteration, I have to go and reevaluate every remaining sensor, right? So it means that whenever I want to place a new sensor, I have to redo basically the entire work again. So that's why, right, this is the number of possible locations times the number of sensors I place. So this can be quite expensive, because I have to go and reevaluate each one again to select now the best one, which would be this one, place them, and again then reevaluate everything. Okay, so this is slow. So now let's work out the algorithm that will fix this, because simple greedy does not work. So the method is called CELF, and this is an algorithm for optimizing submodular functions under cost constraints, right? Last lecture, we were doing this under cardinality constraints. So we were allowed to select a given number. Here, we can select any number as long as it's less than some cost. Okay, so that's the difference. Right, so here is a heuristic you could try out, right? A heuristic that you could try out would be the following. You'd say, let's just ignore the cost. Let's repeatedly select sensors that give us the best marginal gain, and let's keep doing this until the budget is exhausted, right? So I'll be just kind of, if you say I want to maximize you know, you would say I'm given a given budget, and I want to get the most I don't know, like if you are a grad student and you come to a restaurant and you say I want to get the most calories and I have the budget. One way would be is just to say I'll take the dish with the most calories and add it and order it, and then I'll take the second dish and I'll keep doing this until my budget is exhausted, right? That is this strategy. It's like when I select, I only select based on how good the sensor is. At that time I ignore the budget, but I keep doing this until I run out of money. Okay, and this would be one approach. And I'll show you that this can fail arbitrarily badly. It means that there exists a problem setting that is a bit intricate, but for this problem setting, our solution can be arbitrarily far away from the optimal solution, right? So this approach will be arbitrarily bad. So let's come up with an example that shows that this is really a bad idea. So let me show you. So the idea is the following. Imagine I have n sensors and a budget B. And imagine that S1 gives me reward R and cost B. and S1 to Sn give me reward R minus epsilon, but they all cost $1, right? So this would be like, you can order one dish, it gives you 1,000 calories, but costs you $100, or you can order these other dishes that cost you $1, but each one gives you 999 calories, okay? I'm sorry, I am not sure why I came up with this example, but I think it will work out, okay? So, so it's about us being hungry, right? So what would this approach from the previous slide do? You would come and you would say, what's the best sensor to place? What's the dish with the most calories? And you would order S1. Now that you have ordered S1, you exhausted the budget, you get that single dish, and you go home, right? But what would be much better thing to do here? A much thing to do here would be to order these dishes. You could afford yourself 1,000 of them, and you would get 1 billion calories or 100 million calories for $100, right? So it's either getting 1,000 calories or 100 million or whatever I calculated, right? So the point is that in this setting you can fail arbitrarily badly, right? Rather than making the total reward to be B times R, you are only getting the reward of R. And now if you make the B bigger, the difference between the optimal and the R will only get bigger. So we can fail arbitrarily badly, right? So this seems like a bad approach. You can also see that this now points of what might be a better approach. And a better approach would be to do a proper cost-benefit analysis, right? You'd say, what is the best dish? How much calories do I get per dollar spent? And I will just get the things that are cheap in terms of per dollar spent. So you'd say, what is the best sensor to place that maximizes the benefit to cost ratio? So the way you can write this out is to say, at a given iteration of the algorithm, I will pick the sensor that gives me the highest ratio between the benefit, the marginal gain of that sensor, divided by the cost of the sensor. Okay, so I'm kind of saying what gives me most money for the buck, right? Like, what do I get the most benefit for the money I'm saving? I need to pay. Let me show you a different case where again this will fail arbitrarily badly. So even though this seems like a good idea, it can also fail terribly, right? So let me give you an example. So here I have two sensors, S1 and S2. S1 is a super cheap. It costs me epsilon, very little, 1 cent. And then S2 costs me B, my entire budget. Let's say that I have just one outbreak. And let's say that the benefit of S1 is 2 times epsilon, while the benefit of S2 is B. Okay? So now if I do benefit to cost, I'm like, the benefit of S1 is 2 epsilon divided by epsilon is 2. So I get 2 units cost benefit, while the S2 has benefit of B and the cost of B as well. So the ratio is 1. So what my method will do, it will select S1. But now that it selected S1, it can no longer afford S2. Okay? So what does it mean? We get, by selecting S1, we get reward 2 times epsilon. While if we would select S2, we would get the reward of B. Right? And again, if you send epsilon to 0, you get arbitrarily bad solution. Right? And the point here is that this algorithm incentivizes choosing nodes with very low cost, even when slightly more expensive sensor can lead to a much better global result, right? So here, this is intricate because it gets me to spend just a bit of money so that I cannot afford this big sensor anymore. And overall, my benefit is much lower than it could be. Yes?
I think I'm misunderstanding. Why can't we buy B over epsilon S1 sensors?
Because in this case, there is only 2 sensors. There's only 2 nodes in the network. You can only place you can only buy S1 or you can buy S2. There's no S3. It's a very, not saying this is realistic, but you know, I could come up with a more intricate one, but it's a super simple one that shows it fails. Yes?
So basically what you're saying is that you buy like a sensor which doesn't really cost too much, but seems to be like very attractive, and you can't, then under the greedy, you can't really afford to use a sensor which potentially could be much better in the long run.
Correct. That's exactly. Because you are greedy, you make something that locally looks like a good decision, will leave you a lot of budget free, but then this becomes all of a sudden too expensive for you. Yes?
So we're essentially trying to solve a knapsack problem, but it'll become more challenging because the sensors will affect the cost of other sensors, or the benefit of other sensors as we place them.
Correct. So that's a great insight, right? Like, we are kind of trying to put as many sensors into our budget, but the hard part here, or the interesting part here, is exactly what you said. It's a very good insight, right? It's that sensors kind of interplay each other, right? Like, adding a sensor changes the benefits of all other sensors. So it's hard because it's not just fitting as much into the knapsack as possible. We are also all we carry is in some sense the benefits, and the benefits play off one another. That's a great insight. All right, good. So it seems we failed twice. Here's a surprising fact. The surprising fact is that the CELF algorithm says the following. Says, let me run the two algorithms we just saw fail terribly. Let me run them independently. So I will run the benefit cost greedy that we just saw, and I will get a solution. I will use the unit cost greedy, where I ignore the cost, to get another solution, and my algorithm will produce the two sets, S prime and S double prime, and return the one that gives me greater benefit. Okay? Is it clear what I'm doing? I'm running the first algorithm. I'm running the second one independently. They both give me solutions, and then I return the solution that is better out of the two. Okay? So I'm kind of running two imperfect algorithms, and to the user I'm returning the better one of them. And what's the surprising fact? The surprising fact is that these two independent runs of two imperfect algorithms gives you a near optimal solution, right? So the theorem one can prove is that this strategy is near optimal, so you achieve a solution that is 1/2 1 minus 1 over e of optimal, right? So this is for cardinality constraint maximization of non-monotone submodular functions. Now I get 1/2 here, right? Why is this surprising? It's surprising because I use two algorithms or two approaches that each one of them can fail arbitrarily badly. But if I take the better of the two, then I have an optimality guarantee. So it means that when one fails, the other one does well, and when the other one fails, the first one does well. So together, they actually work quite well, right? So that's the surprising observation here. Yes?
Is it at each step you evaluate which solution is better, or
no? You really run. You produce two independent solutions. You run one, you run the other. You run benefit cost until you exhaust the budget. You run the unit cost. So when you select, you ignore the budget, but you keep running this until you run out of budget. You get two separate solutions. You return the one that is better, and that's it. Okay? Good. And as I said, this is super cool because now we all of a sudden have a good algorithm out of two crappy ones. Okay? Great. Any questions? Yes, go ahead.
If CELF finds the argmax of f of s prime and s double prime, wouldn't that mean it's at least as slow as like kind of running both of them individually?
Exactly. So the runtime of this will be the sum of the runtime is you have to run one and you have to run the other. So kind of the runtime is twice, or right? Like you could think of it if each of these, if you assume each of them takes the same time, then running this guy takes twice the time. So it is a bit slower, yes, because I have to run both of them. That's a good point. Yes?
And can we we show in the same way that we showed that each of them individually runs arbitrarily badly, can we show that this one actually does not run arbitrarily badly?
Yes.
Okay.
I mean, it must be true, right? So, because I get this guarantee regardless of what the input problem is. This is over all input problems. So I can come up with an input problem, then one guy will fail. So this means that the other guy will have to be at least this good, right? And the other way around. Yes?
Why the guarantee is different than the one that we derived last time?
Why? Yes. I try not to explain it. I don't want to prove it, right? But the point is, you get the factor from the submodular function optimization, and you get a little constant from the fact that you are taking two kind of suboptimal solutions. But it's clear where this comes from. I will not prove this. I'm happy to point you to the paper. All right, just in the interest of time. Okay, so this is what I wanted to show, what we did so far. So I have a few more cool things to show you. So now I want to show you how to speed up this type of greedy hill climbing approach. Okay, using what is called lazy evaluations. So, and you will learn about this. This is actually a term that's used in computer science algorithms quite a lot. And if something is lazy, it means you only evaluate it when you need it. You only compute it when you are forced to compute it. You don't just compute it because it's fun to compute. And this way, you save time. Okay? So here's the observation, right? So we want to do greedy hill climbing, either the benefit cost one or the unit cost one. It doesn't really matter. The way these things will work, right, as I said, is they will be very slow because at every iteration we need to evaluate all the sensors we haven't yet selected, right? So we start with no sensor selected, we evaluate the reward of each one of them, pick the best guy, put them down. Now we need to reevaluate the marginal benefits, the rewards of all other remaining sensors. So the rewards become invalid, and we go and evaluate them, and again, pick the sensor that gives us the highest marginal benefit, place it, and again, invalidate these rewards, reevaluate them, and keep doing this. And as I said, this is slow. So here is a way how to make this faster because of the submodularity property. So here I have a big slide that I will try to explain slowly. Right? So imagine that I have already placed I sensors, and now I'm trying to place sensor I plus 1. Right? So let's say I have placed sensors S1 to Si, and now at time I plus 1, I'm searching to select a sensor Si plus 1. And how do I select it? I select the sensor U that maximizes the marginal benefit, right? I say I have the sensors S1 to Si. Now I want to add sensor U to it so that the marginal benefit is as large as possible. Okay, that's what I want to do. And I will define this notion of delta sub I of U to be the marginal gain of a given sensor at round I. Okay, so delta sub I of U is simply the benefit of U when I add it to the solution S sub I that includes the first I sensors. Okay. Now, what is the fact? Because of the submodularity property, the following statement is true. So what does this statement says? It says that the marginal benefit of U when I add it to S sub I is bigger than the marginal benefit of U when I add it to S sub j when I is less than j. Why is this the case? This is the case because S sub I is a subset of S sub j, right? These capital S's are these increasing sets that include all the sensors plus the new one. So capital S sub I is a subset of the capital S sub j, right? And because this is a subset of that, and because F is submodular, this is just the submodularity definition. That's why this is true. Okay? So here is now the observation. The observation is that for every node U, delta sub I of U is greater than delta sub j of u. Okay, so what does this mean? This is essentially delta sub I of u, and this is delta sub j of u. Okay, it's the marginal benefit of node u when I add it to placement I, and this is the marginal benefit of u when I add it to placement j. Again, for I less than j, because S sub I is a subset of S sub j. Okay, there's a lot of notation here, but the bottom line is the following. The bottom line is that marginal benefits of nodes only shrink as a function of I. Okay, so that's the main insight. So what this means is that if at some round my sensor u would have this large marginal benefit, and now I place a few more other sensors, and I come back to sensor u and ask it, how much marginal benefit do you have now? The marginal benefit of u will only shrink, right? Because, you know, activating node u in step I helps more than activating it at some later step, right? So by submodularity, it says, you could say, when does selecting sensor u helps the most? Selecting the sensor u helps the most when no other sensors are placed. And as soon as I place some other sensor and then ask, how much can you detect now? It will only detect that much or less, right? So the marginal benefit of u will only shrink as I place other sensors. Okay? Yes?
So we can skip any ones that are worse than the best one in the round so far.
Exactly. Exactly. That's the insight, right? The insight is, let me explain what you said, right? So the insight is the following. This is now called lazy hill climbing. And the idea is that this delta I will be the upper bound on the maximum possible benefit of a given node, right? So the idea will be that we will keep an ordered list of marginal benefits from previous iteration and only reevaluate the benefit of the node for which we have the highest delta I, and then reorder and prune. So the idea is the following, right? At first iteration, I'll go evaluate the benefits, I'll pick the best guy and add it to my placement. But now I will sort the rest based on the marginal benefits at round 1. So I reorder them, right? And now these serve as upper bounds on what is the largest possible benefit of sensor D when I add it to node A, because I know its benefit will only shrink. So now I evaluate the benefit of node D. Let's evaluate, and let's say that now this is the benefit I get. So now I know I don't get to select node B. I can put it down. And I can go now to evaluate node B. And let's say the node B says this is the benefit of it being added to node A. Now I know I can stop. All right? Why is that? The reason I know I found the maximum guy is because I know this is an upper bound. So this will only shrink. And because this upper bound is less than what I already have, I know these guys will only shrink. I already found the highest marginal benefit guy. And that's essentially it. So I can stop and I can place, right? And now, you know, in the third iteration, I would go and evaluate this guy. And I would see where it falls. And if it falls above this one, I already found the maximum one. If its marginal benefit would be smaller, I would have to reevaluate this one. And this would again only shrink. But if it shrinks less than this much, I have found the best thing, right? Because these marginal benefits only shrink, so I kind of have the upper bounds on how much sensors may help. Okay? And what is here to say? Of course, in the worst case, and I think this is your homework problem, in the worst case, you can design these benefits in such a way that it's always the smallest guy who wins. So you have to go all the way to the bottom and then resort, and again go all the way to the bottom and resort. So it can be very nasty. So basically the point is that in the worst case, this optimization won't work. It will be as slow as the greedy. But in reality, it works much faster. So for example, what I try to show here is the number of blocks or sensors we place versus time. This is exponential growth if you say, let me try all pairs of sensors, all triples of sensors, all quadruples of sensors, right? You can never do that. This is now the naive greedy, and you see that essentially it's kind of scaling quadratically. And then this is the CELF, which is with the lazy method, right? And just to go back, why is this called lazy? Because we only evaluate the marginal benefit of the node when we have to. Kind of we evaluate it on demand rather than just going through the entire list. And this is why this is called lazy. Yes?
Every time we evaluate it, we only compare it to the node right below it.
Exactly. Whenever we evaluate it, whenever we know that one is up to date, I need to compare it to the next guy. And because I know that this next guy will only shrink. So if I'm already bigger than the next guy, I know I'm the biggest. And that's the core of the idea, right? Because these deltas serve as the upper bound, as the upper estimate of the best case how much this sensor could help. And if I have a sensor whose benefit I have just recomputed, and its benefit is the best possible benefit of the next sensor, I know I have found the one with the biggest benefit, so I can stop. That's the idea. Yeah, good question. Thank you. All right, good. So the point is, this works really well in practice and makes a huge difference. So this was number 2 I wanted to show you. Any questions? Right, kind of, you got the idea. These benefits shrink, so you can use this lazy evaluation, this on-demand evaluation, to not need to go all the way down the list. That's essentially the trick, and you use priority queue to always be able to find the largest, the one with the largest delta. All right, good. So this was topic number 2. So now I want to do the topic number 3, which is derive this notion of a data-dependent bound on the solution quality. Okay? Here is what I want, how to think about this. Right? So we already know that greedy algorithm from the, let's say, previous lecture has this 1 minus 1 over e bound, basically the worst case bound. Right? So this is the worst case over all possible inputs. Right? So regardless of what is the input data, we know we'll never do worse than that fraction of the optimal solution. What we want to do next is derive a different bound that the value of the bound will depend on the input data as well. Right? So on easy data, greedy hill climbing might do better than 63%, the 1 minus 1 over e. Right? So if the data is easy, the greedy may find me an optimal solution. But if the data is very adversarial, I know greedy will never do worse than 1 minus 1 over e. So the question is, can I say something about the solution quality when actually I get to see the input data? That's the question, and we are going to derive this. Okay? So here is the data-dependent bound, right? So suppose S is some solution, right? We got this solution S somehow, and S has cardinality less than k. And let's say S, f of S is monotone and submodular. The assumption we already had through the rest of all of the lecture. And let's say that I have this optimal solution, P of where I will denote it by T1 to Tk. So these are the k optimal sensors to place, right? Finding this optimal solution is MP hard, but let's say we know it, and sensors T1 to Tk are part of it. Then let U be let the delta of U be the marginal benefit of how much does U help the placement S. Okay, so delta is the marginal benefit of U with respect to the placement S. So let's say we will order these deltas in such a way that node 1 helps the most, node 2 helps the second most, and so on. Right? So I'm kind of just deciding how to name the sensors so that the first guy helps more than the second guy, and so on and so forth. Okay? Then here is the claim. The claim is that the f of the optimal solution is less than f of s, so what I already have, plus the sum of the marginal benefits of the k nodes with the highest marginal gain. Right, so I say let's go from 1 to k, where k is the cardinality of my solution set S, and I say that I take the marginal benefits of the nodes U that have the highest marginal benefit. So I basically take a sum of the k largest marginal benefits over the solution that I have produced so far. Okay? Notice a few things. First, this is a data-dependent bound. Why is this a data-dependent bound? Because this depends on the data, and this depends on the data. So I need to have data to be able to evaluate f. Notice that this bound holds for any algorithm. I made no assumption how s is being generated. It can come however we like it to come. So there is no assumption on the algorithm that generated s. Just to make sure to say, right, for some inputs, this bound can be very loose, can be actually worse than the greedy bound. So at this point in time, the bound becomes useless. So let me now try to derive this expression to give you some insight why is this true. Okay, so let's go slowly over this. Right, so the claim is that I have this delta of u to be the marginal benefit of u with respect to s. I will label sensors u in such a way that delta 1 has the highest marginal gain, node sensor 2 has the second largest marginal gain, and so on with respect to displacement u, displacement s. And my claim is that the value of the optimal solution is less than equal than the value of the set s plus the value of the marginal gains of top k largest sensors, right? Marginal gains with respect to s. That's the claim. Now, how do we prove this? F of optimal is less than f of optimal union s. This is due to monotonicity, right? If I have some sensors and I add more sensors, I don't decrease the quality of the solution. I only detect earlier. So this is kind of trivial. The way what I do now is I will take this f of opt union s, I will subtract s and I will add s. So this is now the same as I had before. And now you should remember that in the last lecture we took this expression and we were able to prove that this expression has the following value. Right? So basically what we proved last time is that the marginal gain of the entire set is less than the marginal gain of the elements in the set, right? So meaning that this is now the marginal gain of the optimal solution over s. So, and this total marginal gain is less than the sum over the elements of the optimal solution, the marginal benefit of each of these elements. This is what we proved last lecture, and here is this f of s, which is here now, right? So from here to here is due to the submodularity, right? And essentially what this is saying, this is marginal benefit of opt with respect to s, and this is less than the sum of the marginal benefits of the individual entries of opt with respect to s. And intuitively, this makes sense, right? So this is this one. Now, what do you notice? You notice that these are really deltas, right? This is the definition of delta of T sub I. Definition of delta up there. So rather than summing up the deltas of the nodes in the optimal solution, because I don't know who's in the optimal solution, I will just sum up the largest deltas. Okay? Give me some life, some sign of life. Okay, clear? Right? This is what's the benefit of something in the optimal solution. I don't know who's in the optimal solution, so I'll just take the biggest deltas I can get. Right? So this sum will be bigger than that sum. So yes?
I think you maybe align the third line to the fourth line. Isn't that just sort of the definition?
This to this?
The third to the fourth. That one to the 100.
Yeah.
That's just the definition. That's
oh yeah, sorry. Yes, I'm too far. Yes, I'm too far. Great, good point. So these are the deltas of TIs, and now I'm ahead of myself. I don't know what this is because I don't know who's in the optimal solution. I just take the deltas that are the largest. Okay, great, thank you. Yes, I was too fast, right? From here to here is just a notation. From here to here is the inequality. Because these benefits are from the nodes in opt. I don't know who's in opt, so I'll just take the biggest I can find. Okay? And this is exactly what we wanted. F of opt is less than f of s plus the sum of the biggest gains. Okay? Great. So this is what I wanted to show you theoretically and algorithmically. So now I want to give you show you a case study and show you how this works for water distribution and then also for blogs. So I showed you this picture before. This is a water distribution of a real city with 25,000 nodes and 25,000 pipes. And then using a cluster of 50 machines in a month, people were able to simulate 3.6 million scenarios. So 3.6 million contamination scenarios, which is basically pick a random location, pick a random day, pick a random time of the day, simulate the scenario, right? Because the water flow dynamics depends on where you start, what is day of the week, it's a Monday or a Saturday, versus what is time of day, morning or evening. And the way I will show you here now is, this is the number of sensors we place, and here is the solution quality. Higher is better. This is our hill climbing, the quality of our hill climbing solution. And then the offline bound would say that the optimal solution is somewhere between blue and red, right? So if this is wherever we are, if this is the worst, if this is 63%, then this is 100%, right? So this is just this value divided by 0.63, and we get up here. And we know that the optimal is somewhere in this band between red and blue. If you now compute the data-dependent bound we just computed, the data-dependent bound is the green line. Okay? So what's the point? The point is that the data-dependent bound is much tighter, meaning that using the data-dependent bound, we know that the optimal solution is now between green and blue, not between blue and red. So this means now we can be much more confident in the quality of our solution. We know that the gap is this big rather than that big. Okay? So this is how the data-dependent bound works in practice. It gives me much tighter bound. It gives me much higher confidence in the quality of my solution. So I can be more confident that we actually found something that is quite good. The second thing I want to show you is that doing this optimization, for example here, trying to reduce the amount of population affected, directly optimizing the objective function using the machinery we talked about, gives you much better than trying to use some heuristic, right? So for example, what are some heuristics? You could say, I'll put sensors on high diameter pipes. Doesn't work at all. It's actually even worse if you say, I put sensors where the flow is very large, right? So basically, it's not okay because you just put them in one part of the network. If you put sensors where the population is, where the people are, it seems to be working better. Then this black line with circles is random, and then the blue is based on the degree, right? You say I will put it at big junctions, right? So random is not that terrible, right? What's the benefit of random is it kind of uniformly covers the space, right? So random is not that stupid as you may think, actually, right? And then this is the solution. And there was actually a competition that was run called Battle of Water Sensor Networks, and there was a number of participants. And this was some score in how many examples the approach won, and it was better than some supercomputing based approach from Sandia and some other places. And basically, it was just this greedy optimization on a single machine and all the machinery I showed you. And I should just say that the paper that developed the algorithms and all this just got Test of Time award at KDD, and Test of Time is an award that people get 10 years after the paper is published as the most influential paper of the last 10 years, right? So this had a big impact in the community. Another thing I want to show is that depending on what kind of objective function you want to optimize, you get different types of placements. So for example, here by detection likelihood, I mean we want to detect as many scenarios as possible. If that's our goal, then the sensors are kind of placed spatially uniformly, more or less. While, for example, if I want to minimize the amount of population affected, you see that most of the sensors are here because here is the most population. So I care about detecting it where the population is the densest, and in the parts where population is sparse, I put relatively few sensors. Yes?
Our detection likelihood payoff function gave us no penalty for the time at which we detected it. And
correct.
So in this real-world example, is that really particularly useful? Because we essentially just put them at the most downstream locations, and then 15 days later, we finally see it, but we only see it after it's affected like most people, right?
Completely good and valid argument you're making. I agree. You should talk to EPA. Right? I mean, they came up with these three functions, and objective functions, and I agree that kind of this one to me makes the most sense. But in some scenarios, maybe you have a contamination that may not be life-threatening or something, but at least you'd like to know that you've been compromised or whatever was their motivation. I cannot speak to that, but everything you said, I agree with you. Okay, and then the benefit of CELF, of lazy evaluation, again, exhaustive enumeration, greedy, and then the lazy greedy. And then the green lazy greedy is where you just compute the solution, and the red one is where you compute the solution as well as this data-dependent bound, so you know how far away from the optimal solution you are. Okay, and again, you get this huge performance benefit. So let me finish the lecture here. I think I kind of covered everything I wanted. If you guys are interested, there is an S set of slides to talk about which blocks to read. It is just another use case of kind of the same algorithmic technology, and rather than trying to speed up and cover it, you guys can cover that yourself if you are interested. Another thing I will say is that these submodular functions are extremely useful whenever you have any kind of problem where you try to cover some space. And one place this is very useful is in recommender systems, where you try to have diversity, right? So you could say, I have a set of movies I want to show to the user, and movies are from different genres. So the question is, what movies do I select that are most relevant to the user, but also cover all the genres, right? And the same, this kind of submodular function optimization is very important there as well. So in many recommender systems, you have these types of submodular function optimization methods run to increase diversity of the results you see. So it's a very general and a very useful framework to think about covering the space of possible possibilities. So with this, we are done. Thank you very much, and see you on Thursday.